Hi, you'll be pleased to hear this is only a short one, but probably less pleased to learn that the reason this is only a short one is that it will allow you to have done all the work necessary in the first proper homework. So you've got a couple of hours of homework to get done, and one of my normal worksheets that I would paste up for you. And this is the last bit of content that I might even consider putting into your PPE. We haven't finished particles. We're going to go on to strangeness next, but I shan't put any strangeness into the PPE exam. I shall only put in particles up to annihilation and pair production. Okay, annihilation. You probably all know from science fiction, etc., that when an antiparticle meets its particle opposite, the two destroy each other, releasing energy. The geeky amongst you, and of course that's all of you, because otherwise you wouldn't be doing A-level physics, will know that that's how the Starship Enterprise runs, by mixing together the matter and the antimatter. Anyway, the real process is what's in this diagram here. I don't know who drew these diagrams, but I've pinched them, they're quite nice. Is that our antiparticle and our particle meet. Obviously, our antiparticle and our particle are usually going to be oppositely charged, which means they're going to attract each other, so they are likely to meet. And they annihilate. They completely destroy all of themselves. And of course, that's allowed because they're going to have opposite quantum numbers. So if this were an electron, for example, then this would be a positron, and this one would have a +1 electron lepton flavor, and this one would have a -1 electron lepton flavor. This one's got a -1 charge, this one's got a +1 charge. The quantum numbers are all opposite, and so the quantum numbers all add up to 0. And once we've annihilated the two particles, the quantum numbers are still 0 because we've got a pair of photons. So annihilation is perfectly allowed within quantum mechanics and within particle theory, and happens all the time. But perhaps slightly different to what everybody in sort of science fiction tends to think of as antimatter meeting matter. You only get annihilation when the particle meets its opposite. So when the positron meets the electron, or when the proton meets the antiproton, or all of those kinds of things. It's not any old antimatter meeting any old matter. And the other thing that I perhaps ought to mention that's a quirk is that this scheme here, to a positron meeting an electron and producing two photons, is the simplest annihilation that can happen. The two electrons are the lightest charged particles, and so this is the most straightforward annihilation that's going to occur. And the result is two photons. There have to be two photons because otherwise you can't conserve momentum and energy. If you think about it, if there were only one photon and the one photon fires off up here, well, what happens to the momentum, because a photon does have momentum whilst it's traveling, what happens to the momentum that's in this direction? We've got to have two photons in order to allow us to conserve momentum and energy, and those things are still required. So anyway, what was I saying? Yeah, this is the simplest. And if we were to crush a proton into an antiproton, we might well see a much more complicated spray of particles. And those of you who've been paying close attention might even have spotted that in the previous video. You could even go back and have a look at the previous video and see that I've actually included in a picture taken using photographic emulsion of the track of a proton meeting an antiproton, and that sprays out a whole pile of particles. It sprays out pions. And the reason that it sprays out a much more complicated thing than this diagram here is something we're going to cover later on, which is that protons are actually composite particles. They're made up of other stuff. An electron or a positron, as far as we can tell, is a singular thing. There's nothing on a smaller scale within an electron or a positron. That's not true for the proton. And so as we get the heavier particles, the particle hitting the antiparticle will still result in those two particles being annihilated, but it won't necessarily result in something as simple as two photons being fired out. Nevertheless, your course treats the annihilation process as just this diagram. Okay, so you and I know, because we're good physicists, that, and we paid attention to those pictures that I put in the last video, we know that a proton meeting an antiproton, for example, is going to do something more complicated than fire out two photons. But as far as your course is concerned, if a proton meets an antiproton, they're still going to fire out two photons. Okay, your course doesn't treat the annihilation process as any more complicated than this very simple one that I've got here, which is the simplest possible, which is the result of an electron meeting a positron. All right, I hope that makes sense. Just this diagram you need, really. You need to remember the content of that diagram. Whatever antiparticle and particle the exam will choose to give you in an exam question. Now, the key thing is that energies must be conserved. Therefore, the rest energy and any Ke of the particles beforehand, usually when we consider annihilation, we're only talking about slow-moving particles. You might remember when I was talking about sort of the detection of particles, we talked about them being slowed down by the process of ionizing particles that are going past and by the process of Bremsstrahlung radiation before they meet something and annihilate. Okay, so we normally don't have a big Ke before when we're considering annihilation. We could have, but we don't normally. So the rest energies of our particles beforehand must equal the rest energies and the Ke after. But of course, if we're making photons, a photon's got zero rest energy, so it's just the energy of the photon afterwards. So the rest energies before equal the energy of both photons afterwards. Now, could they include Ke into an exam question? Ke before? I've tried. I've tried saying, you know, the electron and the positron were moving at, you know, 3 × 10⁷ meters per second beforehand, and had a look at what effect that makes on the resulting photons. And the answer is it barely has any effect at all. For the Ke before to have an effect on the energy of the photons that come out afterwards, then the electrons, the electron and the positron, have to be moving at relativistic speeds. And as things moving at relativistic speeds aren't on your course, no, I don't think the Ke before can actually turn up in the exam question. Because the highest the speed could be going at is 3 × 10⁻⁷, because we say it's not relativistic up to about 10% of the speed of light. So 3 × 10⁷, when you work out the Ke due to that, it's pretty insignificant compared to the rest energy. The only way the Ke gets much more significant than the rest energy, or even on a par with the rest energy, is if the particles are travelling at relativistic speeds. As I say, that's not my course. So we end up with this. Twice the rest energy of one of the particles, because of course they're a particle and antiparticle pair, and one of the key things about particle-antiparticle pairs is they have the same rest energy, they have the same mass. So twice the rest energy of one of them is equal to the energy of the two photons. Now, even the most mathematically illiterate of you, you know, the Jareds of this world, he'll hate me for saying that, will spot that we can get rid of the two twos. Obviously, the Elliots of this world, they haven't spotted it because they're too busy talking, but you know, you can get rid of those two twos, but don't. The exam board has a tendency to expect you to write that there's two of them on both sides of the equation at the beginning, so that you're showing to the examiner that you understand what's going on in annihilation. You understand you've got two lots of rest energy of electrons, the electron and the positron, and that you've got two photons coming out the other side. So the examiner expects to see those twos in there to begin with, because the examiner wants you to show that you understand what's going on in annihilation. So include those twos to begin with. We all know you're going to cross them out, but include those two twos to begin with, please. Make sure you get all the marks in the mark scheme. Right, and sorry, I've scribbled all over the bit I wanted. For our electron and our positron, that's half an MeV. Two lots of half an MeV gives us two photons. So if the question said, find the wavelength of photons produced by electron-positron annihilation, what would we have to do? Well, we've got two lots of half an MeV. Remember, it's an MeV, mega, so we've got to include a 10 to the 6. Remember that it's in EV, but we only do calculations in joules. So I've got to multiply by 1.1 times 9 times. That should be 1.6, shouldn't it? 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19. In order to convert it from electron volts into joules before we do the calculation. And remember also that it's easiest, if you've been asked to find the wavelength, to start off with the wavelength equation. Don't start with HF and then have to remember to convert back at the end, because so many of you forget to convert back at the end and thereby lose marks. If you start with lambda in your equation, you start with HC over lambda as your equation for photon energy, then you get to the answer more convincingly. So there's our starting equation. Obviously we rearranged that, still got 1.9. I promise I didn't put 1.9 into the final calculation. Maybe. And there you go, you get something like that. And 10 to the minus 12 picometers. Obviously, it might actually be 2.3 if I've used 1.9 throughout. So that's annihilation. Calculation is not difficult. Just remember, put the twos in to begin with, even though they cancel out, just so that we know what's going on. All right, nothing hard about that, I hope. Annihilation questions are really hard. You just have to remember what to do. So we move on to pair production. Yeah, this is just stolen straight off Wikipedia. I don't even bother writing this. The picture for this is here. So pair production is a really high energy photon. A really high energy photon comes somewhere into the field of a nucleus, and in this diagram, that again I've nicked from Wikipedia, I've called the nucleus is called Z. So our photon comes somewhere within the electric field of Z. That means if it suddenly becomes charged particles, Z can feel the influence of those charged particles because it's got an electric field, and Z can take away some of the momentum and up here receive some recoil. Because if we're trying to do this without a nucleus being nearby, we couldn't satisfy both conservation of energy and conservation of momentum. Actually, in free space, this process is happening all the time, but it's happening on speeds faster than Heisenberg's uncertainty principle, and so they're all virtual. For actual real positrons and electrons to be made in pair production, we do need a nucleus nearby. This isn't normally drawn like this. It's not normally drawn including the nucleus, and I'll show you a drawing of what it looks like in the next slide. I've put the nucleus in because it is sometimes an exam question to say that pair production occurs when the high energy photon comes within the electric field of a nucleus. So this bit sometimes needs saying in order to get all the marks in the exam, even if the diagram isn't actually drawn like that. So I've sort of put it in there to hopefully try and remind you to put it in the exam. This is more like what you would normally draw if you were asked to draw what's going on in pair production. High energy photon, and the photon is then converting its energy into a particle-antiparticle pair. And just like annihilation, because the particle and the antiparticle have opposite quantum numbers, we haven't broken any conservation rules. by making a particle-antiparticle pair. Our photon really needs to be a higher energy than the rest energy of the two of them, because if it's the same energy, they wouldn't have any Ke and they would instantly annihilate, and so therefore it wouldn't really happen. So the photon has higher energy than the rest energy, combined rest energy of the two of them, which is what that says. So, typical question would be this: what's the minimum frequency of a photon must have to be able to produce a positive and a negative muon in the proximity of a nucleus? So the most typical question is an electron and a positron, but we've just done an electron and a positron example for annihilation, so I thought I would change it and make it a pair of muons. Now, of course, that means that our photon has to be 207 times more energetic than it was to create a pair of electrons, because we remember from earlier on that the muon is 207 times heavier than the electron. So what the answer to this must be: the minimum energy of our photon must be 207 times the minimum energy necessary to do electron-positron pair production. But anyway, let's follow through the maths. So the rest energy of our two muons, our positive muon or our negative muon, is 105.7 MeV. So our single photon this time, because it's the arriving single photon, is equal to the two lots of muon rest energy. It's in MeV, so we add the 10 to the 6, and I remember to call it 1.6 this time, so at least I've got this one right. That rearranges to that. And hopefully when I push the numbers on the calculator, I get that. Who the hell knows what 10 to the 21 would be? 51 times whatever 10 to the 21 is in letters. Who cares? 10 to the 22 hertz. 5.1 times 10 to the 22 hertz. An enormous frequency, well above anything that we would ever normally think about, but perfectly possible when we're talking about the kind of energetic events that happen in the top of the atmosphere when cosmic rays, high energy protons, smack into the top of the atmosphere. Okay, so that one's pair production. Nothing really to pair production or to annihilation. So just quickly in summary, when a particle collides to its anti, they annihilate. Simplest annihilation produces 2 gamma photons. The opposite process is pair production. That's 1 gamma producing a pair. You have to have a nucleus nearby. And the photon pair must have an energy greater than the total rest energies of the 2 resulting particles. All right, I hope that's all relatively straightforward. As I say, pair production and annihilation is the last thing that might turn up on the first big set of formal exam questions, which I'm going to set you as a homework. It's mostly going to be beta decay, but there may be 1 or 2 questions on this in there as well. And as I've also said, this might just turn up in the PPE if I can find some questions to use. Strangeness and particle colliders, which is where we're going to go next week, will not turn up in your PPE.